before I'll give you more examples today, there will be a few more examples, but before we do that, I'd like to discuss this relatively simple topic. We can cover it straight away, even with this little knowledge about linear maps. It says this, again, if I have two vector spaces, two vector space quadruples like this. Oh, I just realized I said linear spaces. I haven't used that before, and I said it actually in my first slide as well. It's linear spaces, actually, that's the synonym to the vector spaces, even though probably I never said that before, so let me just let's just say it the way it's supposed to be. That's the vector space, the term we use most often. So on my first slide, when I said linear spaces, I meant if I said so. I don't remember, did I say so? Yeah, I did say so. I meant vector spaces. So imagine I have again two vector spaces, and imagine now in one of them, in the domain, I have a basis. In such a setting, and that's the setting which will prevail in most of the questions in this, actually in all of the questions. I say most of the questions in the yellow book, because linear spaces which don't have a finite basis, that's a linear spaces which don't have finite dimension. We'll have plenty of such spaces. For instance, C1 space, on my last example on the previous slide, it's an example of such a space. It's a space which doesn't have a finite dimension. It doesn't have finitely many vectors which will serve as a basis. They are much harder to study. If those of you who will continue your mathematical development, you will see that later. In this course, we only concerned with the finite dimensional vector spaces. In that case, we have this very nice theorem, or lemma. I know you like the term lemma. It says this: if I have two linear maps with the same domain and the same codomain, so one of them I will call T, the other one I will call S, two linear maps with the same domain and codomain, and you see the domain is finite dimensional, we have a basis. So these are linear maps. And we know that these two linear maps such that their values, they coincide on the basis vectors. So T of x1 equal to S of x1, T of x2 equal S of x2, and that is true for any element of the basis, T of xn equal S of xn. If I know such things, in a finite dimensional setting, the conclusion will be that actually T delivers the same value as S on any vector V. Effectively, that means that T is identical to, that's a typo again, identical to S. So in the finite dimensional setting, two linear maps, if they match on some basis, they will match everywhere. Which means effectively we need to know the values of my linear maps only on the vectors of some basis. It's a great advantage. One of you came to me on Thursday and said, why do we need span and basis? That's why we need them. It's one of the reasons why we need them. If I want to study a linear map in detail, I don't need to study this linear map everywhere. I just need to study it on the elements of some basis. And that's just finitely many values to study, actually. So here's the proof for that. It's a very straightforward proof. All you have to do, you have to just carefully use the definitions of every term involved. Look at this. If I start with a vector V, in my vector space V, I can say first that because B is a basis, it means that every vector admits a linear representation in terms of such basis, right? So it means that we have a scalars, lambda 1, lambda 2, lambda n from my field of scalars such that my vector V is representable as a linear combination, like so. Is a linear combination of elements of my basis. So if I now compute T of this vector V, representable as a linear combination, I can sub in my linear combination, use a substitution, lambda 1 x1, lambda 2 x2 plus dots lambda n xn. By a linearity, because it's a linear map, it's something, one of the elementary properties I established on my first slide via mathematical induction. I can say that this one can be given as a linear combination of the individual values. Here we go, lambda t of x1, lambda 2 t of x2 plus dots lambda n t of xn. This is bilinear. This step is justified by linearity of t. Now, because of these identities, which I will mark with the asterisks, because of these identities, so by these identities asterisks, I can say I can replace now every factor here, t of x1, t of x2, t of xn by s of the same vectors, s of x1, s of x2, s of xn. And now if I use the linearity again in the opposite direction, I can now say that the combination of the values of a linear transformation, linear combination of the values of the linear transformation, it's the one single value of my linear transformation in the combination of vectors. Lambda 1x1, lambda 2x2, lambda n xn. This step is justified by linearity, but this time of the mapping S. And that is this can be shortened to S of V, because that's a representation for V. So you see we just proved that T of V equal S of V, and that is true for any vector V. You see my original choice for V was pretty random. I haven't put any restrictions on V. I said just choose any vector, and the argument worked. And that's the finish of the proof of this little lemma. Like I said, it's a very straightforward lemma, but it's a nice exercise to put things together in a nice structural, logical way. Any questions?